Okay, so welcome back. We are in the final section of chapter 4 of sheaf theory through examples, where this chapter as a whole is looking at the issues in topology, providing us a background for understanding the spaces over with which sheaves will associate data. And this section actually presages the next chapter on sheaves by hinting in its final paragraphs as to the role that these topologies play within a sheaf context, and arguing that sheaves can be viewed as a sort of continuous functor from a category involving a topological space of some sort, like a Poset, a partially ordered set, or pre-order involving a topological space, into data. And they're sort of continuous functor because they honor limits in that context. And that's a very powerful and high-level notion indeed as to what sheaves are like. And they argue that it's, Rosiak, the author, argues that it's a bit like continuous functions. But to discuss that, we need to talk about this core issue of continuity, this idea of a continuous function. And as introduced here in section 4.3.3, that's our focus. And page 141 of Rosiak's book, Rosiak notes that the idea of continuity at an intuitive level is that if x is approximately equal to y, so we say a function f is continuous if for an x given approximately equal to y, f of x is approximately equal to f of y. So it preserves closeness. We say that a function f is continuous if it preserves closeness, right? It honors closeness. Things that are close together at the start are close together when f is applied to them, right? Of a function f, this should say of a function f, this idea of like, okay. Poorly phrased, but I think you get the idea. Now, one of the points that I think it's important to make is that if we just have sets, a set is a jumble of elements, of points, with no structure on them, right? There's no structure within a set. There's no sense of one thing is closer, one element is closer to another within a set. A set's just a sack of elements, jumble of elements, a heap of elements. And there's no sense that one is closer to the other. There's no ordering between them. There's no added structure for a set. It's just this bag of disconnected elements. And so talking about a function that's continuous in mapping set X to set Y and saying that a function is continuous, or say set A to set B to avoid confusing up here. There's no sense that like certain values in A, set A, are closer than other values. So there's no sense that like one element of A is close to another element of A, and therefore when we map them over to B, that the results have to be close. There's no sense of that at all. There's no sense of closeness to be preserved with a function from just a set A to a set B with no added structure. But as we've seen in this chapter, we have added structure for topological spaces, right? A topology is associated with a set X but it imposes more structure on that set, right? It's not just a set. It's the set with some added structure because these axioms are fulfilled. And particularly, I just note that it defines relationships between sets in terms of what the different subsets are, and the fact that we have some sets that are the union of others, or some that are the intersection of others. Do you remember that? Remember this notion? So this describes the structure of a topology in terms of some relationships, much like in a category, the role that an object plays is shaped by the relationships, its morphisms into and out of it. Here, we have kind of relationships between morphisms, as it were, between these sets in the topology, right? The topology consists of the set X, but also the set of subsets of this that have this structure. Do you remember that? And do you remember more than that? Although it was a little bit hand wavy, we argued that, look, if there are certain things that always appear together, they either neither appear or they both appear. They either don't appear, neither of them are present, or both of them are present. There are things that always appear as a unit together, say Edmonton and Calgary. We can view those as, in some sense, in this topology that's shown here, being close. They appear, wherever one appears, the other appears. In any set that has one, it has the other. If a set doesn't have one, it doesn't have the other, right? So this is a topology, for example, where we might informally say these two, Edmonton and Calgary, are close. And in that sense, the topology is capturing some information. There's capturing some notion of closeness. There's also a notion of intersection of these sets that says, in some sense, these two are shared by both of these, that they straddle both of them. You could perhaps think of it as. Okay, so I'm just reminding you of this sense that with a topology, we have more information than a set. With a set, from set A to set B with no added structure, it doesn't make sense to talk about continuity. But with a topology, it does make sense to talk about continuity because there's a sense of closeness. There's Larissa. So maybe one of you could let her in here. Okay. Hi, Larissa. Good to see you. So within this discussion, we're going to be talking about this notion of closeness for a function between topologies, between topological spaces. Okay. And specifically, we're going to talk about this formal definition that for topological spaces X and Y, a function going from X to Y is deemed continuous if for every subset open, every open set in Y, remember these are X and Y are topologies, right? We could have written X comma tau X and Y comma tau Y, right? These are accompanied by topologies. These are topological sets. They each have a topology, right? Are you comfortable with that idea? And we're saying, what does it mean for a function to be continuous from topological space X to topological space Y? Given that we have this added structure, it does mean something. For a set, it would be meaningless. If X and Y were just sets, it would be meaningless. Here, there's a meaning to it because we have some sense of closeness. What is that notion of closeness? Well, it's an abstract notion of closeness, but we'll see it makes sense in terms of intuition. So a function from topological space X to topological space Y is deemed continuous if that function, and it should say F, I don't know what, why I omitted that F here between those two. Come on. If for every subset open set in Y in the topological space for Y, the pre-image of it, the things mapped into it from X and from X, form an open set in X. So let me repeat that again. If we have topological space X with a set X and a topology, say tau sub X, and topological space Y with a set Y and topology tau sub Y, a mapping between them, a function between them from X to Y, is a continuous function if for every open set in tau sub Y, in the topology associated with Y, the things that map into it from X, the things that are mapped into it from set X, are themselves an open set in the topology for X. And I think we'll draw something on the board for this, but I want to note that there's no notion of a metric here, right? There's no notion like there's some delta and some epsilon and it lies within that. But it's actually a mapping that preserves the notion of closeness, that preserves this notion of two things being close together we just talked about. Two things are close together if they appear in every, either they appear together, whenever one appears, the other appears. So let's talk about this a bit more. So I'm going to erase this. And equipped with the red marker and the Ki blue, we will see if we can sort of have a little drawing here. Okay, so this is going to be my topological space X, and I'm going to write it explicitly here as a pair of a set X and then tau sub X. Tau sub X, you remember? Mm-hmm. This is, yeah, it's a subset of the power set. Do you remember that? The power set of X. And therefore it consists of different subsets of X, right? That's what the power set of X is. It's the collection of all subsets. And this was a subset of them, right? So maybe it has in here. Something like maybe it has here something that, so maybe we'll say that X here is A, B, C, D, something like that. What do you think? And we'll say that I'm tempted to make it like, yeah, okay. I'm not gonna make this too fancy. Do I want to? This will be what set am I drawing out implicitly? Power set. Yeah, I was drawing out the power set, although that would be for three elements. Maybe I'll say maybe we'll do something like this. So we'll have A, B, C, D as one set. Does this have to be there? It does. The set X has to be. What else has to be in here? Empty set, right? Well, I'll try it like that. And then we're going to have another collection of subsets, but they have to abide by some consistency, right? What are those consistency rules? Remember? Yeah. The intersections of them. So whatever I have, they're intersections, finite intersections. So if I do it for 2 of them, for 3, for 4, any finite number, that has to be present. And what else has to be present? Their intersections and their unions. They're arbitrary unions, right? Arbitrary meaning you can't even have it. I mean, if this were an infinite set, it could be an uncountable, infinitely large, number of unions, right? Okay, so here we go. A, B, C, D, and here we have C and D, and maybe to spice it up a bit, I will have A, C, D. What else has to be here besides empty set? If A, C, D is in here. Sorry, A. Yeah. Okay, A has to be here because the intersection, right? Right? Is this a valid topology on this? It is. It is. It's a valid topology. And we could write it out. I'm going to write this as, this is actually a category. Yeah, you may remember, this is a few pages later. This is actually a category. And Rosiak writes the category. I'm gonna need help from Jeff and Larissa particularly. He writes it with this, I think it's a script O. But it's sort of at the limits of my possible understanding how to write it. I didn't know what character it was.
Oh, I always thought it was a Q.
Yeah, it's a weird an upside down Q. Yeah,
It's an O with a off.
that's right. It has like it has a cowlick.
Pretty hair. There's a pretty hair.
Yeah, it is a cowlick, I think. So there's actually a theorem in topology. Do you know? Maybe it's algebraic geometry. In any case, that you cannot comb a sphere without a cowlick. Do you know that? So if you have hair on a sphere, you can't like comb it without some part sticking out. Which is kind of interesting. Okay, so is this a valid topology? And now I'm going to have a set 1, 2, 3. Right. Right. Okay. And this is going to be the discrete topology. So tell me what this will be then. What 2 things are always in it? Yeah, the full set and the empty set, right? And then what other combinations need to be in here? What other things need to be in? If this is the discrete topology on this, in other words, the maximum fine-grained topology, what would it need to be?
1, 2, and 3.
1, 2, and 3.
Each one of those is element 1, element 2, element 3.
Yeah. 1 and 2.
Oh yeah, you do that order too.
1 and 3.
He wants to do that construction.
Right.
And 2 and 3. And then
And then
what is
the single element.
the signal out? Okay, sorry, I'm imposing rotini on you again. Okay. This is a category, so we'll call this Y. Topology on Y. And this will be the, it's a category of opens for Y. These are sets and inclusions. So in other words, this set is included in this set is included in that. Are we okay with that? Okay. And now the idea here is that we're going to have a mapping here that is going to map set X into set Y. And it's going to do some mapping on and again, if it were just a mapping from the set to the set, there's no notion of continuity. Like there's no notion because X by itself is just a jumble of elements. Y by itself is a jumble of elements, no closer, no, and so there'd be no way we could judge for this function itself. Is it continuous or not? So I will write it this way. I will write it 1, 2, 3. We will have 1, A goes to 1. B goes to 2, C goes to 3, and D goes to 1. So that's a mapping. We can't say whether that's continuous or not, because A and B aren't closer in a way that would allow us to assess whether they map to something that's closer. But this is more than that. This mapping is more than that. This is a mapping of topologies. And you're going to tell me, based on this mapping, where these go. So where does the set ABC go into? Well, it's going to go into, so A is going to map to 1, right? B is going to map to 2, and C is going to map to 3. And maybe what I'm going to do, just because it's going to be awkward to draw it this way, I think what I'm going to be doing, I think it's going to communicate it much better if I draw it. So these are our topologies, just to remind you. And we're going to need to refer to them. So this is our set X. I'm going to start using the PI tool. So there we go. And this is our Y. We good with this? Maybe this is a dumb coloring. Maybe I should be more fine grained, more coloring. Okay. So we're going to have this is our set A, B, C, D. I'm just drawing it like these are things in a bag. There's no order. This is our set 1, 2, 3 with no particular order, right? What does this mapping look like on this? What does the mapping look like? Well, where does A go? Where does B go? 2. Where does C go? 3. And D goes to 1 as well. So I'll go something like this. Are we okay with that? Okay. Okay, now. I'm gonna try something. Okay, so first of all, we'll just assess whether this meets the criteria for a continuous map of topologies. What this is going to say, this criteria for a continuous map of topologies is, so this of topological spaces, excuse me, it's going to be continuous if for every open set of this topology, tau y, right? If for all open sets V in tau y, what's the criteria? What does it have to be? So I'm just setting this up to have a criteria for whether this is a continuous map. And what is the criteria? It has a criteria involving for all open sets V in tau y, what? The pre-image, also called the inverse image of F on V must be what? Must be an element of tau what? X. Yeah, so in other words, if this is an element of tau x, right? Right? I.e. inverse image of V must be element of tau x. Okay, so what that's saying is that when we say inverse image of V, all the things that map into, so let's consider V to be 1, 2. All of the things that map into 1, 2. Well, what are all the things that map into 1, 2? What set? So if we consider 1, 2, and Y, what set maps into that from X? What set of things in X map into 1, 2? Sorry? A, B, but D as well, right? A, B, D maps into that, right? And what this is saying is that for all of these open sets here in Y, if we consider all of the things in X, the set of all things in X that map into those, that has to be an open set over here. Are we ready to examine this? Okay, so I'm going to ask you what maps into the set 1, 2, 3? A, B, C, D. Is that an open set here? What maps into the empty set? Well, there's only one thing that can map into the empty set. Empty set. Anything else, it wouldn't be a function, right? It wouldn't be a function because a function has to assign for everything in its source something at a target. And if this were anything but empty set, it wouldn't be able to assign something at its target, an element at its target, right? Okay, so those are so far so good. How about for 1? What are all the things that map into, well, I'm going to say for 2, or no, say for 1. Okay, fine. Any of these that will fail. So for 1, which one, what will map into 1? AD. Is AD an open set of this? No. All right? It's not an open set. How about for 2? What maps into 2? Is B an open set? No. What maps into 3? C. Is C an open set? Ain't no open set. How about 1, 2? ABD. Is that an open set? No. It's AB and a CD, but not ABD. ABD is all but dissertation, but okay. 1, 3. What is what's the inverse image of that? What are the things that map into 1, 3? ACD. Is that an open set? Yeah. That would work. 2, 3. Is that an open set? I'm sorry. Is the inverse image of it an open set in X? BC, no, it's not. So you could see this actually fails the continuity test. Because there are some things that map into this that don't form open sets here. Okay, now I was thinking about actually drawing out like these different divisions, like ABCD would be this whole one, AB would be this one, ABC, ACD would be like this one, and A would be that one, but it would be a bit cumbersome. Okay, so this is not a continuous function. It's not a problem of it's not inherently a problem that shows up when we consider how it maps sets. It's a problem that shows up when we consider how it maps the topologies. But inspired by one of the videos I had suggested in my slides, this wonderful video by Elliot Richardson. I wanted to provide some intuition because this may seem a little bit opaque as to like, why does this have anything to do with preserving closeness? Like you can apply this, but like intuitively, the notion of continuity is that things that are close in X have to be turned into things that are close here. And it's not obvious like why this criteria realizes that, like, helps judge that. So I'd like to walk you through Elliot Richardson's wonderful little demonstration of that, if I could. So you'll recall just a few minutes ago, I said that at an intuitive level, we might say, well, things are close together over here in one topology if they always appear together. Are there any things here that always appear together and never appear separately? They always appear together, in other words. If one appears, the other's there. If one is not there, the other's not there. C and D. C and D are here, they're here. Neither of them is here, so that's fine. Neither of them is here, that's fine. Neither of them is here, that's fine. But they're kind of like a building block. They're kind of unit to go together, like Calgary and Edmonton in that early case. And so intuitively, Elliot Richardson notes that, look, intuitively, we'd expect kind of, we have if we have something over here in a tau X, and we have one point in a tau X at another point in that same tau X, we might here, if they always appear together, we might consider them kind of close. Okay. And the hope is at an intuitive level that this will map over here into tau Y. such that these things are close here. Okay. So we're going to call this X, this one X, and this one X prime. Okay.
Rotate the camera back.
Like
Yeah,
Up.
yeah,
up here.
yeah.
Is there a glare issue?
Yeah, there is a little bit. You want to adjust the light?
Okay. Okay, great. Can we still see? Okay. 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 So this is maybe F of X, and this is maybe F of X prime. And we hope that they'll map together here, that they're close here, they always co-occur, and they will map over to Y in a way that they co-occur there. They'll be in the same open set here. Okay. Or they'll be together in any open set where one occurs, they will appear there. Okay, and so Elliot Richardson walks through this nice little proof where he's demonstrated that. I'm going to see if I can recreate that idea. Okay. Okay, so the idea here is, look, suppose we have an X, and an X prime here over in our source, some sort of source set here. So we're going to call this a set. We'll just say this is our set X. Okay. So we have that. Right. And we're going to talk about how these are mapped to Y. And what we're hoping is that they will map to things that are close in Y. That sort of, when you have one, you have the other. You always see them together. This is the hope. Okay. Let's see if I can recreate this. So we're going to consider this problem in light of this. So suppose the key important part of this reasoning is we're going to say, well, look, suppose this is the case. Great, thanks. Suppose this is the case. We're going to show that it follows that both of these are going to be in Y together. So suppose that we take this abstract definition that we've been struggling with, which we understand how to apply, but it's not clear like why it like preserves closeness in this intuitive sense. But let's take as a granted that that's the case. And what he showed, and what I will try to show, is that if you take this as a given, and if you take it that X has two things that are close in X, they always co-occur in X, and all the open sets, no open set excludes one without excluding the other. They're so close, you either an open set includes both, or it doesn't include all. It misses both of them, right? That's the idea. And the idea is, okay, so if we have an open set which have these two things that are close, we're going to see why this abstract definition implies that they are. No. The water bottle is segregated, deliberately so, purposefully segregated. Okay, we're going to see why this abstract definition combined with the fact that they're here in X implies they're both in Y. Are we ready to see this? Okay, so if this abstract definition applies, and we say, well, look, we have f of x here. We're going to say, well, look, we know, okay, f of x is an element of y, right? And we're going to consider the pre-image of this thing v that this is part of. So f of x has been mapped over into some open set v, right? It's an open set v, right? In y. That's what the abstract definition said. It's an v is an open set in y. So imagine that we consider the open set v into which f has mapped x. Are we okay with that? So x has gone over here and mapped to this guy here. Okay, we okay with that? Well, what do we know? What do we know? Well, look, we know, so this is our v, and this is in tau sub x, or tau sub y rather, right? The v and y. Okay, and what I'm going to say is, okay, now we could consider the pre-image of this, right? Pre-image of v, that's part of this definition, this abstract definition up there is pre-image of v, right? Let's consider the pre-image of v. And we are saying that the pre-image of v, we've accepted that this abstract definition holds. So the pre-image of v, this thing here, is an open set over here in X. Okay? It's some open set over here in X, tau sub X, that contains X. But, and so this implies that X is an element of F on its one of V, which is an open set. This is an open set in tau of X. Are we okay with that? That X itself is in some open set. That's what we accepted through the abstract. We say the abstract definition holds. But now we're further positing that in X, there are two things that are so close that if X is there, X prime has to also be there. Okay, so that must mean if X always has X prime when X is present, and X is present in F minus 1 of V in this open set over here in X, then X prime has to be part of that too. Like X prime must also be there. Again, let me retrace it. This may seem, you have to be careful about what you're assuming. We're assuming that we have a situation X where we have two things that are close, X and X prime. We're trying to intuitively see why does that mean they both have to map to an open set over here. Okay, that we want to see that this intuitive picture holds, that they're close here, therefore they become close here, that they co-occur here, they co-occur here. And what I'm saying is to see, and it's not clear originally to us why this abstract definition showed that, held that, implied that. And what I'm trying to show you is, look, if we accept the abstract definition and we consider a situation where X and X prime are so close, they always, they either are there together or they're neither are there. If we consider that situation, and we have a situation where X is present in a tau X, it maps over to F of X here in some V of in tau Y. And we consider what's the inverse image of where it appears. It's the tau X. We're accepting that this is true, this abstract definition. So there's some open set tau X here. That's what this abstract definition says, that for any V in tau Y, there's tau X here. But we've already said that X and X prime always co-occur. So if X is present, X prime has to be present. So X prime also needs to, X prime must also be present in tau X. It has to be present here as well, i.e. X prime is an element of this. And look, if X prime is an element of this, this says that F of X prime, if F prime is an element of F to the minus 1 of V, then it's implying that if X prime is a member of that open set, of that thing that is mapping to V, then F of X prime must be in V as well. I mean, that's what that would mean, right? Like if F prime is in the preimage of V, why is it in the preimage of V? It's because X prime is mapped into V. That's what the preimage is. It's the set of all things mapped into V. So this means F of X prime must also be present in V. And what I'm saying is, if they co-occur here, they co-occur here for any tau prime, any open set for which this is true. If we consider F of X maps into tau, this tau y, or that tau y, or that tau y, the same argument holds that the preimage of that is an open set. And if X is there, well, we know X is there because F of X was mapped into this thing in our V. Then if X is there, because we posited they always co-occur in delta X and tau X, then they must be there together. And that means that F prime has to be present in this same target open set. So this holds for any open set to which, X could map in, then it follows that X prime must also map to that open set. If these things are always co-occurring, either both are there. If X occurs, then X prime occurs in any open set. It's there. So what I'm saying is that this rule, while it looks very abstract up here, well, it looks totally disconnected from notions of closeness. One thing it implies is that if X and X prime always co-occur, if Edmonton and Calgary always co-occur, if C and D always co-occur, then when and we have a continuous function, it follows that their mapping to 1 and 3 must always co-occur in Y. That's right. That's right. That those are always going to co-occur over in Y. The mappings of both of them are always going to co-occur. That's right. So that's what it is saying here. And yeah, so that they must co-occur. Yeah. Now this is interesting. Now here, let's look at this. So let's consider this, right? For two things which co-occur. What we said is, look, if we posit that X and X prime are close in X, in the sense of always co-occurring, then they must be close in Y. Let's consider whether this is the case in our case. And I haven't looked at this. I want to scrutinize this for our mapping. Okay. So we consider C and D. C maps to 3. D maps to 1, right? Okay, so maybe I'll take a photo of this before I okay, now I'm really in trouble. I'm gonna quickly wrap up here. Okay, here we go. Okay. This is hardly like a Rembrandt, but I want to say, take
It's
a
also
photo.
in the Zoom.
What's that?
It's in the Zoom. I took a picture of it.
Okay, that's great. Thank you. Okay, so now let's consider where C and D can map to. Here. C, well, we know C maps to 3, D maps to 1, right? So the question is, if we have C mapping into 3, okay. Okay, so we're going to assume that C and D always co-occur here. They either both are not present or they're both present together. And that seems to be true, right? Then we're going to ask, do they, for any set in topology Y, which does abide by this, or do they always co-occur? Is this, so in other words, for any mapping F that is continuous, they have to co-occur. Is this a map that's continuous? No, we said it was not. Let's try to create a map that would be continuous. If we could. Can we do that? Let's do a map which is going to be, and I'm trying to think where to do this. This is an obvious place here to do it down here, right? Okay. Okay. We're going to, this is going to be a set 1, 2, 3. Are we okay with this? 1, 2, 3. What thing is always present? Well, 1, 2, and 3 is always present, right? I'm going to do the most simple one to start. This is the indiscrete topology, right? So let's follow this. Okay. So if first of all, is this a continuous map here? So same map, F. With respect to this mapping of topologies, so if this is our Y, call it Y prime, tau Y prime, is this mapping X to Y prime with F, as topological spaces, is this going to be continuous? Well, let's see. It says for each and every one of these open sets in Y prime, right? The inverse image of it, or the pre-image of it, same thing, is an open set next. So what's the inverse image of empty set? Empty set. Is that in X? Yeah. What's the inverse image of 1, 2, 3? What are the set of all things that map to 1, 2, 3? Well, A maps to 1, 2, 3, B maps to 1, 2, 3, C maps to 1, 2, 3, D maps to 1, 2, 3. So it's A, B, C, D. So that's in here. So this would be a continuous mapping. Now let's see, does it abide by this rule on continuity? Are you ready to see this? For continuity. Are things that always co-occur here, C and D, they always co-occur. Neither is present or both of them are present, C and D. Do they always co-occur here? Well, sorry, and their mapping always co-occur in the target topology. Well, look, what's F of C? It's 3. What's F of D? It's 1. Do 1 and 3 always co-occur here? Yeah. So far, yeah. Okay. So now let's do another one, which is finer grained. So there was this one. Maybe, I think we've kind of gotten our mileage out of this. So I think we could safely erase this. Okay, so here we're going to have y double prime tau y double prime. Are we okay with that? This is going to have 1, 2, 3 automatically. We know that it must. That looks like a weird bracket. It has to have this. Let's suppose we have let's suppose we have 1 and 3. Well, maybe I'll do something a little bit richer. I'm going to have 2. And I'm going to have 1 and 3. Are we okay with this? Okay, first of all, by the definition, the abstract definition, is this continuous? Is the map here going to be continuous? F with respect to this mapping of these topologies is going to be continuous. Well, we just have to say, okay, we have to go through each open set here and ask if the preimage of it is a what? Open set next. Okay, so let's just do it. Is it for the full set here? Is it an open set? Yeah, it's an open set. We did that before. Is it for the empty set? Yeah, it's an empty set. How about for 2? Is the preimage of 2 an open set? B is not, right? B is not an open set by itself. So that actually would not be, dude, I'm going, just so we can finish early, I'm going to amend this. What could this be other than 2 that would let this be that it would let it be continuous? Well, that it wouldn't pose a problem for this one. If this were what? This were 1, 2, but then we need an extra one that's like 1, right? This is starting to seem a little bit familiar. Yeah, the intersection has to be there. Okay, so we need 1. We need 1 here because that's the intersection of these 2 things. And then we need empty set, right? Okay, so, and these are preorders, so we have this nice inclusions. Don't forget, these are nice categories. They warm the cockles of my heart. Okay, so, okay, so for 1, 2, is the pre-image of that an open set in X? Okay, 1 and 2, ABD is not. Okay, so what would it need to be? It would need to be erased. It would need to be erased. So yeah, so we're gonna, okay, let's come up with one that would be continuous. You help me. You help me here. Help me, folks, help me. Okay, so
Having said because we need AB.
If we had 2 and 3, that would mean B, C have to, okay, those can't go together. 1 and 2, it's going to be ABD would have to be together. This is 1 and 3 would be ACD, which is there, right? So we could actually have 1 and 3 here. And oh, this is rather pleasing. is this a topology? Empty set 1, 1, 3.
Just keep adding.
It is a. Okay,
But.
but it's not. This one's going to pose problems. But wait, we could not have that. Okay. Okay. Right? Okay. Would this be, well, you could start to see like continuous means something here. Like continuous is a real constraint. Like the reason we were having trouble is because of this rule that we need the reverse image to be the inverse image, the pre-image to be an open set here, right? That's what gave us some trouble. So so is this continuous? So it is for the total set, it is for the empty set is 1, 3. Things that map into 1, 3 is A, C, D, and that is an image here, right? Okay, so now this continuous map. Now let's say, does this preserve closeness in the intuitive sense? Does it preserve if things go together over in our source topology, that they go together in our target topology? Okay, so things that go together here, C, D, co-occur. They're a building block. Does their mapping always occur? C maps to 3, D maps to 1. It either occurs together or it doesn't occur at all. So what we're saying is this, for this case, it is continuous because it maps some. It's just gloms everything together. Everything comes together, or not at all. Here, it's a little bit more discriminating, but it keeps 1 and 3 together because they have to be kept together here for it to be continuous. So it maps close things to close things here, in the sense that close is they always occur together or not at all. So this abstract notion, while it may seem kind of bizarrely arbitrary, it actually guarantees co-occurrence maps to co-occurrence. Because it has to apply for every open set for which these things map. They both have to be in the pre-image over here of that. And that's what was giving us trouble as we tried to do that. Does that make sense? Okay. Okay, so that's a little bit on continuity. And one thing that helped convey is like continuity is not a trivial thing. Again, it doesn't come in at all in the map between sets. It's not about whether F from set X to set Y has some magical property in and of itself. It's with respect to a mapping of topologies, right? On X and on Y, because the topologies capture the structure of this situation. Okay, so I have to start preparing for a meeting with federal partners that occurs at 1 o'clock shortly. But I want to say that, okay, preserves the structure of topology. It honors closeness. It turns close things into close things, just like this. And given continuous functions, F and G after F is continuous. If F maps, if F maps X to Y and allows open sets at Y to be dragged back, as it were, to open sets at X, and then there's mapping G from Y to Z that allows open sets in Z to be dragged back to open sets in Y, then you can drag back things from Z all the way back to Y. Okay. Right. There's another. Okay, so there's a category called top, top. The category of topological spaces and continuous functions between them. Each object here is a topological space, you know, a set X together with its open sets, tau. And morphisms are functions X to Y that are continuous. So these are continuous functions, right? So continuous functions in the sense we've just discussed, continuous functions X to Y. You could think of them as things that honor co-occurrence. You could think of them as things that abide by this mapping, the pre-image, you know, if it maps to an open set in Y, the pre-image of that open set is an X. It honors the structure of the topology. And you could think of it as related to like pulling back this square. You might think of this as like X, this is Y, and this is an open set in X. This is an open set in Y. And what we're doing is we're able to, if we have these mappings, this maps an open set into an open set, and so we can pull back from this open set and get an open set in X. This should remind you of some of the diagrams with like a pullback square. This is a pullback square, a Munich square. And you may remember this type of diagram where this is a subset of this is a subset of this. Okay. Okay. So there's a functor going from a contravariant functor going from this category of topological spaces to posets that basically maps topological spaces, objects here, into objects here, which are posets. The posets of their open sets, the preorders associated with their open set. Poset and preorders are very close. It's just, I think, isomorphic things get collapsed in one and not in the other. But morphisms between topological spaces turn into morphisms between posets in the opposite direction. So a map between topological spaces X and Y, which is really X comma tau X, Y comma Y tau. A map between that induces this, because this is contravariant, a map between posets of the associated with their open posets from Y to X. Remember contravariant functors? If you map from a morphism here from X to Y, it maps it into something that goes from the image of Y to the image of X. That's why it's contravariant, right? Okay. So we talk about this poset of open sets. Probably I should have put this for any topological space X, there's a poset of open sets for that topological space, specific to the top. And in fact, I drew them on the board. That's what we're looking at in the board. That's what I was showing on the board here, was posets for each of these topological spaces. And I said, remember, they're a category where the objects are sets, the morphisms are inclusions, where this is a category associated with, so I even wrote the name up there, open of Y, and that's is the poset of opens of X. These are all categories. Those are a category specific to a specific topological space, like we've just seen. Okay. So the objects are in this poset. Each object is an open subset of X, right? That's what those open sets are. And morphisms are inclusions of one and the other. That's what we drew there, right? Like why one is in 1, 3, or what have you. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, Now, Daniel Rosiak comments that if we have a family of these underneath a given open set, that open set is there. So if we have a U, and then we have different V's that are included in U, that's what this is. This is a monomorphism, meaning this is a inclusion there. It's like these are sub pieces of this, right? These are like the sub pieces beneath it. So we have a region U, and it might be broken into V1, V2, V3, and the overlaps correspondingly, like this one here. This is from Daniel Rosiak's, right? Book. And so this entire space U, or this entire open U, like this one right here on the board that we just drew up here, this one, that's composed of these, and it's the union of them. But you can describe that union as it's a colimit. Why do I say it's a colimit? Can anyone remind me? Colimit, it's like push out. Why is it like a push out? Why is it like a, what's that? Glue them together. At certain points, they're the same. So like V1 and V2 here, for the region of V1 intersection of V2, they're the same. So it's not like V1 and V2 put together like tinker toy pieces next to each other, a round thing and a rod. No, it's like they're stuck together at a certain point. They overlap, right? And we don't double count this. This is V1, V2, including their overlap, considered the same. Just that's what push-out does, right? It considers, you take like this causal loop diagram and that one, and you consider these vertices and these edges, these lengths to be the same, and they're overlapped. Okay, so here we might imagine this U as kind of this is our Poset, so it's two with the opens, and it has all these different areas of overlap. And this is something that we've talked about, like here, where we have different provinces and subset of provinces, right? Or these where we have certain things that always co-occur. This is this idea, like with CD always co-occur, Edmonton and Calgary always co-occur. If you have one together in this Poset, you always have both. Okay, so to be finishing up here, like Daniel Rosiak does, with some comments on sheaf. So what Daniel Rosiak says is, look, at the end of this, look, a sheaf. So we're basically poised to be able to understand what a sheaf is. A sheaf is going to be a continuous functor from this category, like on the boards there, or the category associated with these open sets associated with a given topological space. It's a functor from this into a data space, most traditionally set. So it's going to assign data for each of these regions of the space. And it's going to assign a function between those data, if it's mapping it to set, called a restriction map from this one to this one, or this one to this one, or op of it, depending on which one you're doing, where this projects down into that. Okay, so, but not only that, it's the limit of these to make sure that all of them commute. They're all abided by nicely. And Daniel Rosiak argues, look, a continuous function in like calculus or real analysis or what have you, this is like a function that preserves limits. So if you take the limit of some sequence, like 1 over, I don't know, you do like 1 divided by 1 plus 1 divided by 2 plus 1 divided by 4 plus 1 divided by 8, and you take that, and you apply this continuous function f to that, that is the same as applying it to each element of that set and taking the limit of that. That would be a continuous function. As we say, it commutes with the limit. You could have the limit inside and take the function of that limit, like 1 divided by 1 plus 1 divided by 2 plus 1 divided by 4 plus 1 divided by 8. It approaches a limit of 2, right? Gets closer and closer, like Zeno's paradox, closer and closer. And if we apply f to 2, that has to be the same as applying f to 1 plus, and f, not plus, but f applied to 1/2, and f applied to 1/4, and f applied to 1/8, and then taking the limit of that sequence. If those are the same, then we call the function continuous. And really, a sheaf is like a continuous functor from this category of opens, or like one of those on the boards, into data that is just like that. It honors all of these mappings, and it makes all of these commute in a nice way. That basically means it's consistent in how it treats all of these. It gives a consistent picture on how it treats all of these. You may recall that from 2 times ago that you can turn a open cover, like geometrically, into a simplex like this, or simplicial complex, and it has a category associated with it. Remember this, where like this corresponds to the whole triangle, the 2 simplex. This corresponds to this edge of it. This corresponds to this edge. This corresponds to this edge, etc. Well, sheaves are very close to being the limits over this mapping from the simplex into this, that basically, so that for each of these vertices, each of these edges, each of the 2 simplex, it's going to take the limit of that in a way that guarantees that the data for this vertex, the data for the edge, and the data for this vertex are all consistent. And the data for this vertex and this edge are all consistent. And the same thing for this, and it totals up here. So again, if we have 3 people from this region of Saskatchewan ill, and 5 people from this one, and 8 people from that one, then we should have a total of 16 for all of these, so that it's all consistent. So really, a sheaf is like honoring a limit in the same way that a continuous function honors limits. A continuous function commutes with limits. The function for a continuous function f, function applied to a limit, is the same as the limit of the function. And so it is with a sheaf. So we can go and take the limit in terms of the data assigned to all these things, such that they're all consistent. They all commute nicely. That's something about where we're going. Okay, I need to stop so I can go prepare for this presentation to